talk I'm going to explain the equivalence between the plus version of Egger-Fuller homology and the hermetic contact homology. And this is one where with parallelogy and all of that. So precisely the theorem is the following. You start from a three manifold which is closed or empty, and from a contact structure which is positive and correlated. And then there exists a chain map from the chain group of Egger-Fuller homology of minus m to the chain group of hermetic contact homology of MC, which is a quasimorphism which commutes with the U map on both sides. Quasi-isomorphism. Which commutes with the U map. The U map is defined on both sides up to homotopy. And which takes the contact class to the empty set. And so basically today I would like to explain almost everything apart from the quasi-isomorphism property. So before doing that, let me first remind you that in dimension 3 there is another Floer type homology which is called Zeinberg-Witten-Floer homology that was defined by Colin and Morka. And this third homology was already shown to be isomorphic to hermetic contact homology by Charles on one side, and on the other side isomorphic to Egger-Fuller homology by HUN-REN, Lee, and Charles. And so what I propose today is to explain the third side of the triangle. So the main tool that we will use to pass from one side to the other will be the use of open book decomposition. So I'll remind you what it is. So for me, an open book decomposition of M is a triple S, H, and phi, where S is a compact oriented surface with non-empty boundary, and H is a diffeomorphism of S, which is the identity of the boundary. So out of these two first data, we can construct what is called the relative suspension of SH, which is obtained by taking the product S cross 0, 1 and identifying S cross 0, 1 with the equivalence relation, which is the following. So I put T, the variable, in 0, 1, and so you identify as usual for the suspension H of X 0 together with X1. But in that case, you also, since you have boundary, you also identify yt with yt prime whenever y is on the boundary of S. So we identify all the boundary components to one circle. So in that case, let's say that S times T, that I will denote ST, is called the page of the open book, and the boundary of S times T, modulo the identification. This case is called the binding of the open book. And phi is just an identification of the relative suspension with the manifold M, and usually if you forgot about phi, the identification is understood. Okay, so for example, if you take the open book corresponding to the two disks with the identity, what you get is a 3-sphere. The binding is just the trivial knot in the 3-sphere, and then the page is the foliation or the complement of the trivial knot by disks. So, what does open book have to do with Eckart-Floer homology? Well, the most important remark here is the fact that an open book decomposition gives you an Eckart decomposition of the ambient manifold. So if you start from SH, an open book decomposition of M, you get the Eckart decomposition by taking the first underbody to be S cross 0.5 modulo the relation, which in that case is just the fact that you pinch the boundary of S cross 0.5 to just one curve, and H2 to be the complement. These are two underbodies which are glued. Along their boundary, and the boundary is the Eckart surface obtained by taking S0, the page S0 union the page S1 This is the Eckart surface. So for a picture, you have the following thing. This is one page of the open book. Let's say S0, which is G. And by the open book, you have this vibration, so you rotate S0 up to the opposite position, you get S1 And so the union of these two surfaces gives you a Eckart surface. You have H1 on one side and H2 on the other side. And better than this, from the point of view of Eckart-Floer homology, you can get the preferred collections of alpha and beta curves adapted to this situation. Namely, if you take a collection of arcs, 2G arcs, where G is the genus of S, inside S0, let's say, or inside S, so that S minus A is a 6G bone. Then you have the family of disks given by d alpha equals to A cross 0.5 modulo of relation, which sits inside H1, and d beta, which is A cross 1/2 modulo of relation inside H2. So this gives you compression disks. I will picture them on the editor. And so the boundary of these disks gives you this collection of alpha and beta curves. So the alpha curves are just the curves A cross 0 union A cross 1/2. And for the beta curve, what you get is A cross 1/2 union A cross 1. So just to the boundary of this. But remember that you have the monodromy acting on the page S cross 1, which I identify it with S cross 0. So this is equal to A cross 1/2 union H of A cross 0. And since you want the curve alpha and beta to be transverse, you will take, instead of A here, a small push-off, I will describe, B. So B is just a small push-off of A contained in the surface S1/2. So here is a picture. So I take A here, let's say A1. I rotate here, I rotate it using the open book. I get, so this is A1 equals 0, this is A1 cross 1/2. And so this deformation gives you the disk D1, D alpha 1, let's say. And for the curve B, I will take in this talk a small push-off like this. So there is, so that you minimize the number of intersections inside S1/2. So this is B1. Okay. There is only one intersection point X1 inside S1/2. And then when I go back to the page S0, I apply the monodromy so that I have something complicated like this. On the other side, S0. So this is your special alpha and beta 3. And as you know, to define a Gardner homology, you also need the choice of a base point Z. And I will take this base point Z to be in S1/2 away from the area where I do the push-off. So in this large region of S1/2. Okay? Out of this, so I get a special Egal diagram sigma alpha beta Z. And now I have to recall you how to define the Gardner homology out of this. So for this, I will use Lipschitz cylindrical reformulation of the Gardner homology, which is originally due to HUN-REN example. And for that, you consider that instead of considering sigma, you consider yourself to be the ambient manifold sigma cross 0, 1. This is your Euclidean space. The chain groups will be generated as a vector space over Z2, let's say. So only it's over Z2 by pair Y I. So here I is a positive integer, and Y is a two-jet tuple, not of intersection points, but of chords inside between alpha and beta curve inside sigma cross 0, 1. So without the type small y 1 prime 0, 1, y 2g times 0, 1, where, as usual, while I is an intersection point between alpha I and some beta of sigma I, for sigma the permutation set 2g.
So, intersection, do you consider alpha 1 or intersection?
Okay. So let me draw a picture. So this picture I will put, well, I have sigma cross 0, 1. Which is 0 and 1. I will put alpha curves on the one side and beta curves on the 0 side. And what I consider here are chords from alpha times 1 to beta times 0. Okay. So for the differential, you consider, in some sense, the symplectization of this three manifold. So you consider the manifold R times sigma cross 0, 1. That you end up with a symplectic form ds dt plus omega sigma. So here S is the coordinate in R, T is the coordinate in 0, 1. Omega sigma is an area form for sigma. So let's say this is omega. You also consider some Lagrangian boundary conditions. So the first Lagrangian is L alpha, which is just R times alpha times 1. And beta is R times beta times 0. And now you can, well, you pick an almost complex structure with various properties that I will not describe, but which is compatible with omega, which is also S invariant. For example, so J, an almost complex structure compatible with the situation. And then, for the differential, you will consider, you will say that, well, you will write the differential of y I to be a sum over pair y prime j of some coefficients that I will write like this. Where this counts J holomorphic curve of index, but of a special index which is not the Fedor index of index 1 with boundary in L alpha and L beta, and of course which are asymptotic to y and y prime, respectively plus infinity. So from y to y prime, and the number j just the counter which takes into account the number of times we intersect the strip, the trivial strip r times z times 0, 1. So intersecting I minus j times the strip R times Z times 0, 1. So they look like this. Remember? So this curve can have arbitrary genus. Typical curve will look like this. And so let's say this goes to y1, this goes to y, well, let's say y prime, y prime, this goes to L alpha, L beta, L alpha, L beta. And so you count curve like this. Another way to think about this curve is that you have a projection from R times sigma times 0, 1 to R times 0, 1. And you can think of these curves as multi-sections of this projection. Multi-sections. And this special index implies that you can't index one curve, implies that the curves are in fact embedded. They are embedded holomorphic curves. So this is all for the trigger first side. Now we can move on the ECH side. Remember it's 2 or 3. So open book decomposition and ECH. And so the link between open book decompositions and contact structure was described by Emmanuel Giroux. We have the following definition. Whenever you have a contact structure C on N, you say that C is supported by SH, open book decomposition SH, if you can find the contact form alpha of C such that the red vector field associated with alpha has the following property. It is positively transverse to the interior of the pages, and it is positively tangent to the binding. Okay. So you really have to think that the red vector field on the page is kind of orthogonal to the pages, and when you approach the binding, the red vector field starts to rotate until it reaches the horizontal position of the binding, which is the boundary of the page. And the main point is the fact that every contact structure is supported by some open book. This is theorem Giroux. Every C is supported by some open book with connected boundary, whose pages are connected, with connected binding. So I'm not sure I'm going to use this last property. It's kind of simpler when you try to imagine what we're doing. Okay. So you see that once you have a contact structure which is supported by an open book, you have a kind of control of the dynamic of some red vector field. Namely, you know that the binding is a periodic orbit, and otherwise, basically, the periodic orbit of the red vector field corresponds to periodic points to the monodromy, to the first return map of the red vector field. Okay. So now, what is embedded contact homology? So this is something due to micro-machines. So it requires, for its definition, a contact structure together with a contact form. So you take the contact form alpha, so that its red vector field R alpha is so-called non-degenerate, which means that all its periodic orbits are non-degenerate. Now, out of this, you can define the chain complex, which will be generated over Z2 by orbit sets gamma. So gamma here is a collection of periodic orbits together with multiplicities. The periodic orbits gamma I are simple periodic orbits. And the MIs are the multiplicities, with the rule that whenever you have an orbit which is hyperbolic, MI has to be, let's say, equal to 1 or 0, but by convention, this is in the finite correction, I will take this. Okay? And then for the differential, you symblectization of the manifold M together with the favorite almost complex structure, and you want to count for the differential. Again, some specific index 1 curve with genus from gamma to gamma prime. So when I say that, of course you have to take the multiplicity into account. And again, this index, the fact that this index basically is the Friedel index together with the self-intersection of the curve, and you can check that when the index is 1, the curve is embedded. That's why the homology is called embedded homology. And now, I realize that I forgot something for the HL side, because the important feature of this series is the fact that you have what are called U-maps. So I forgot to talk about the U-map on the HF side. So this is back to HF, sorry. So U-map on HF side. So the U-map on the HF side is defined somehow formally at the chain level by sending a pair yi to the pair y(n-1). But in our case, in order to make this fit inside the cobordism I'm going to construct, I need a kind of geometric representation of the U-map. So instead, I would like to do the following. So I take the point z tilde, let's say, in the symblectization R cross sigma cross 0, 1. And instead of u, I want to define the map u z tilde to be given by the count of I index 2 curves that pass through the point z tilde. So passing through a point is a codimension 2 constraint, so this cuts down the dimension to 0. I can count the number of such curves. And the one result that you need is the fact that the map u z tilde is in fact chain homotopic to u. So one thing that you need is theorem. U z tilde is chain homotopic. And you can imagine that you have the same, you can take the same kind of definition on the ECH side. Namely, you take a point in the symblectization of n, and you can count I index 2 curve passing through this point. So this defines for you a map u z tilde on the ECH side. So now, if z tilde is in R times n, again, we can define u z tilde by counting I ECH equals 2 curves through Z tilde. Okay. So now I'm ready to define the map phi plus for you by the cobordism picture. Nous d'espèces de l'expression, I'm going faster than this.
The gamma there would be like there and
Gamma here is just an orbit set. It's an orbit set. It's not a pair. There is no E. And that's one of the points you have to understand. You have some kind of formal index I on the HF side, but you don't have such thing on the ECH side. So they have to disappear in some sense, and so you have to understand how they disappear. So this is not what I'm going to explain now. So now, let's say 4 CFS CC. So again, I take my contact manifold MC. I take an open loop decomposition SH. And out of this open loop decomposition SH, I have this Hegel surface S0 union S1/2 sigma. So the first thing that I do is that I extend the diffeomorphism H from S0 to sigma. So I have the diffeomorphism H bar of sigma, which is equal to H on S0, and which is the identity on S1/2. Remember that on the boundary of S,
The question was what IH equal to here?
ECH. I thought you were talking about the kind of index. Okay, so again, we have H, which is a diffeomorphism of S, and which is the identity on the boundary. I define the diffeomorphism of sigma to be H on S0 and to be basically the identity on S1/2. In truth, you rather have to take some small perturbation of the identity. Don't worry about this. So you take the identity on S1/2. So now, what you do is you construct the homomorphism in 3 pieces. The first piece is the following. So you consider the following surface. So which is B0. So B0 is like a compact cylinder with one puncture on the top boundary, which I see like as a strip like N. But this is another boundary component of B0. Okay? And over B0, I'm going to consider the manifold W0, which is a fibration over the base B0 of fiber sigma and monochromy H bar. Monochromy means when you rotate around the circle here. So W0 fibers over B0 is fiber sigma and monochromy H bar. And this is one fiber, which is S1/2 and S0. And so this is my first piece for the global design. Okay? Now, I use the fact that H bar is the identity on S1/2. And since H bar is the identity on S1/2, I can glue to this thing a trivial vibration over the disk and of fiber S1/2. So I glue my second piece S1/2 across the disk D2 along this boundary component. Okay, so when you move along this circle, the monochromy along S1/2 is the identity, so it's like a trivial vibration in this part. So you can glue this piece. Okay? And now you ask, what does the boundary of this manifold look like? By boundary, I mean the boundary which is downstairs here. Well, what remains is the suspension of S0 with monochromy H and the boundary of S1/2 times D2. Which means that what you get is exactly the open loop decomposition of N. And so what you get downstairs as a new boundary of W0 union second piece W1 is just N. With its open loop decomposition.
Can you repeat that?
Yeah. First I write it. So let's say the boundary minus of W0 union W1 minus means this one, I don't want to consider that one for the moment. This is n, let's say with its open decomposition. How do you see that? The boundary has two parts. Let me draw another picture. So here is another picture. Another schematic picture. So this thing is supposed to be B0. So you have to imagine that B0 is flat. And you kind of rotate around this axis. And so basically this is the cylinder. Okay? So over this cylinder, I have the vibration with fiber sigma. So this is sigma, which decompose into S1/2 and S0. Okay? And now I say that the monodromy along S1/2 is the identity, so here I can do D2 cross S1/2. So my new manifold is this one. What is its boundary? Its boundary is the suspension of S0, which corresponds to this vertical part here, together with the horizontal part. The horizontal part is boundary of S1/2 times the disk. And so this is the usual picture for the open loop decomposition. Maybe you are more used to see it from the other side, when you have a left chest vibration. Then you look at it from this side, and the boundary, like the convex boundary of the left chest vibration, is also given by the open loops. But here you see it from the other side. And so this is the manifold M. And now to this manifold M, I glue, as you can imagine, the negative syncretization of M downstairs. So the third part is the negative syncretization of M. So I glue W2, which is minus infinity 0 times M. Like this. Okay? This is my cobordism W plus. W plus is W0, W1, W2. Okay? Now, as you can expect, you have to put a symplectic structure on W plus. I will not describe the construction, but it's very elementary. So what you want basically is that you want W plus, let's say omega plus to be essentially ds wedge dt plus omega sigma in this part, let's say. So omega plus here will be basically ds wedge dt plus omega sigma. Of course, here you recognize that the M, which looks like Lagerfeld manifold sigma plus 0,1 times R plus actually. And so we want this symplectic structure here. So in upper part. And downstairs on W2, we want just the symplectization of the contact structure alpha. So this is doable by elementary formulas. Since you want to consider holomorphic curves in this cobordism, you want to put boundary Lagrangian boundary conditions on the remaining boundary, which is this upper boundary. So you do that easily. You take a point in this region, the point P. You take the fiber over P, and in this fiber over P, you have the curve alpha. Okay. Now, look at this expression. The fibers in this region are all symplectic because it's for respect to omega sigma. So you can take the omega orthogonal, the omega plus orthogonal to the fibers, which is basically the plane which is directed by ds and dt. And this gives you a symplectic connection. So let's say in the upper part, we consider the symplectic connection given by the omega orthogonal to the fiber. And then you use this connection to parallel transport the alpha curve along the boundary of B0. And this sweeps out for you a Lagrangian manifold. So you parallel transport alpha along the boundary of B0. This gives you a Lagrangian manifold L alpha. And what you have to understand is that since you parallel transport using this dsdt, if you start here with alpha, when you go back on the other side, what you see is beta, which is h of, or h bar of alpha. So here you have beta, which is h bar of alpha. So you're almost done. Apart from the fact that you want to understand what to do with this formal index I that you see on the Egertfer side. So for that, you say the following. You know that at the point Z, the monotony H bar is the identity. So you can take a section of this vibration in this region over Z, along Z. So this is meant to be, so you consider what we call BZ, which is Z times B0 union Z times D2. Z is inside S1 half, so H bar is the identity, you can just consider this. So topologically, it's like a one function disk. This is BZ. And now you can choose an almost complex structure which is compatible with omega plus, which has a good property at plus and minus infinity, and which makes this divisor holomorphic. And now we can define, of course, the map phi plus by the current of index 0 curves. So we want to define phi plus of y I on gamma to be given by the count of some specific index that you have to define, but which is just like a mix of the index that you have on both sides, which have basically the same definitions. So you count I W plus equals 0 curves with boundaries in this L alpha that go from Y to gamma and that intersect the divisor of BZ exactly I times. And so now the claim is the fact that, first of all, this map phi plus is a chain map. This is relatively standard. It follows from Michael and Todd's study of gluing of holomorphic curves. Notice that the important thing here is that you are in the easy situation because all your curves are rooted on the HF side, which means that they are all embedded. There are no multiple covers. Because on the HF side, you go to J2 of course, which are disjoint. So your curves are injected, somewhere injected near the plus infinity. So you don't have to face any trouble defining these maps. So it's a chain map. can show that it commutes with the UMAP by the usual argument, since now, even on the HF side, you have this geometric definition of the UMAP. So you consider curves that pass with this cobordism that are index 1, or 2, and that pass through a point, and then you move the point from plus infinity to minus infinity. This gives you the chain homotopy of the phi plus composed with U minus phi plus composed with the inverse. Okay? And so this is fine. Now I have to explain you why the contact class is going to the empty set. So remember that on S1 half part of sigma, you add this simple behavior where you have the alpha arc which was like this, and the beta arc, so let's say which is AI, BI, let's say beta I and alpha I, and you have one intersection point, and it follows from word of Honda-Kazase matrix that the point whose coordinates are with xi is the contact class. So the contact class is x1 to x2g 0. It's in degree 0. And so when you want to look at the image of this class using the cobordism map, you want to look at curves in this cobordism which starts from this element. But here you have index 0, so you don't want to intersect the divisor BC. And you can easily check that, so Z is here. If you want to leave this point, you cannot leave it in this sector, so you have to leave it in this sector. But if you leave it in this sector, you will intersect the divisor. So you cannot leave it. And so the only possibility for this is to stay at this point, which means that the curve that you get is only the curve Bx. Now Bx is a kind of divisor Bx1 union Bx2 union etc. So Bx2g. So you have one copy, like a trivial copy of such disk over each of the points, just a trivial curve. And as you see, so this gives you the fact that phi plus, since this divisor don't have any end on the ECH side, the image is just the empty set. So you have phi plus of 0, which is the empty set. So, maybe for those of you who already have talked about this thing, you have heard things about the add versions of these isomorphisms. So how do you get, so from now on we have this map phi plus which commutes with the new map and which has these good properties, but you would like to see that it restricts on the at side to a map which looks like the one you already know about in the previous 3 years. So I apologize for those for which is the first time that they ever see this talk. So what happens basically? Well, the situation is the following. So this is again the cobordism W plus. Here's the cobordism. So here you have the divisor BZ. And basically you know that the chain complex for the add version is just generated by elements of degree 0. So this is the subcomplex of the plus complex. And basically nothing happens on the S1 half side. Almost all the intersection points, apart from the contact class, are inside S0. And so let's pretend for the moment that they are all in S0. And now you know that you want to count holomorphic curves that do not intersect C. So your holomorphic curve on the HF side will not enter S1 basically. And so now the point is that if you take 2J couple of points Y, so that all the coordinates are inside S0, and if you know that you do not intersect the divisor, then it's kind of easy to show that the curve does not enter this region. And so the curve stays in some region which is like this. So the curve stays in this region, and this region is exactly obtained in the following way. So there is another description of the, let's say, the red region. This is the red region. The red region is the following. It's a vibration over this size infinite cylinder. So you have a straight black end at plus infinity and something going down to minus infinity. And you have a vibration of fiber S0 and of monodromy H. And if you know that all the coordinates are inside S0, you know that the curve stays inside this thing. And this is the map phi hat we had explained several times before. And so we know that this map is an isomorphism. And since you know that the map phi plus restricts basically to an isomorphism at the hat level, it's such a map, it commutes with you, then you have some algebra which tell you that the map phi plus itself has to be an isomorphism. So this is for this part. And now, if you want, I have 5 minutes to tell you something on the U map, maybe the U map on the HF side. So you might wonder why the U map, the geometric U map on the HF side is the same as the algebraic one. U map on HF plus, CF plus. So basically, how can you visualize the curve that you meet? Well, so you are looking for curves concerning, for using theta, you are looking for curves in R times sigma times 0, 1, passing through z theta. And so you wonder what this curve look like. Well, basically, what you end with as curve, when you kind of degenerate, they look like this. You want to check the image of y I, let's say. And basically, the curve that will give you u z tilde will be obtained by taking trivial strips over y. So you take just the trivial strips. Then the point z tilde selects for you a fiber. There is a unique fiber which is passing through the theta. Okay. So far this looks like a degenerate curve. You have these trivial strips, you have this fiber, but this fiber, unfortunately, is negative index. So there's no reason it does not exist for J. But then what happens is that you can take this fiber, take this trivial strip, and make the connect sum. And when you do the connect sum, if you look at the index formula, which is the index of a curve, is something like minus the Euler characteristic plus twice the function class plus some kind of mass of some index. When you do the connect sum, basically the chunk class doesn't change, but the Euler characteristic goes up by. So here you have 2G trivial strip. So you do 2G connected sum. Each time you do connected sum, you delete like two disks. So this increased by 2 each time you do the connected sum. And so the index that used to be minus 2g in the end becomes what you want. So when you do the connect sum of this trivial string with this fiber, at least you see that you get at least a homology class which has a good index. And then, so which takes you while I to, let's say, while I minus 1, provided the curve indeed exists and that there is only 1. And how you prove that such a curve exists, you have the point z, and you degenerate the manifold, meaning that you are going to bubble off a disk out of the manifold which contains z. And when you do that, you look at the image of the curve, and what you see is that they have to break into basically something, and for indices reason it has to be index 0, so you know these are trivial strings, and something which is inside here. You have some Green constraints, and then here you can do some kind of homomorphic computation to see exactly that you have one curve exactly where you want, and that is the Green condition that you do. And so you have exactly one curve in the end. And so that's why, and of course, when you do this deformation, you have the chain tree, and in the end, you have exactly one curve which that is, because you take one image of the fiber, you intercept C exactly once. Suppose you have two open maps.
This open closed map that we used to find my class.
Yes.
Suppose I have two open maps.
Yes.
You get something new?
I think this is much more general than just applying in this case. You can do such construction in many cases. You can do that with many ends. I don't know what it is, but the construction is very general. It's like, I mean, this construction, you can see this construction as a going map. On one side, you have the sigma for 0, 1, you have the chords which are coming from the Lagrangian, and you want to glue sigma 0 and sigma 1, and this map does the gluing for you. So this can be generalized as in any situation. This is just a gluing map. Yes?
Can you say something about the index, the IHF?
Yeah. So this index was defined by Robert Lipschitz, and it's basically the same definition that you have on PCH side. So basically, it's something which is a sum. You take a chunk class, and then you have this quadratic form which kind of computes the self-intersection of a curve with itself. So you have to see things at infinity, so that things well behave at infinity. And then you also have the master index which enter into it. And basically in the end what you get is like this, basically the Fredholm index plus twice the kind of self-intersection of the curve. So something computing singularities of the curve. It's like in this edge. It's really just takes the same definition. And in the cobordism version it takes the same definition. You can extend the definition very easily. I'm not sure I'm able to do it like this. It's like an exercise, a nice exercise in algebra. Paolo has a very nice proof of this. But I'm not sure I'm able to do it. Actually, one key point that you use in this exercise is, so for the CF hat, CF hat is identified with index 0, and you use the fact that when you take when you look at the commutation with the U map, you have a homotopy, and in fact the homotopy is 0 on elements like this. So the U map really commutes at this level. And then somehow you cook this in algebra, yeah, I'm not able to take it size to that. So it's very nice. Paolo has a very beautiful presentation of this, but I'm not going to. You can ask Paolo.